Okay, shall we start? So can you listen me? So there is one announcement. Tomorrow there will be a quiz in your lecture, maybe for 15 minutes or so. That will be your quiz towards continuous evaluation before mid-semester. Okay, one assignment is already given to you. So hope you are solving that. That you submit before due date and be ready for a quiz tomorrow. So we will extend our earlier discussion to a generalized theory. So use of more than, that is use of more than one feature. So all the examples, almost all of them were of 1D case. So we can extend this to n-dimensional case. So that will be generalization of the theory. And we have seen mostly two category problems, that is classes are two that can be extended to k number of classes. Then introduce a more general error function or loss function. So that is the generalized theory of what we have seen till now. Now a few terminologies you must understand, you can note down this. So features, if they are of say d dimension, say small d is the number of dimensions. So x is input feature or the feature vector which is to be classified. It's a collection of features. So x is a collection of features. Maybe this is height, this is width, say maybe depth, and so on, up to say n number of, or d number of features. If there are d number of features, so this will be a d-dimensional vector. So we represent this as x belongs to Rd, that is, it's a d-dimensional feature vector coming from real space of d dimension. A finite set of category C, so say there are C number of categories, we can write them as omega 1, omega 2 up to omega C. So omega is, or omega I represents ith class in my problem. Now there are set of actions alpha 1, alpha 2, alpha L. So alpha stands for, or alpha L stands for Lth action. And the lambda, we call lambda as loss function. So lambda for alpha I when true class is omega j. So I will explain this. This is loss. When I take say action alpha I when true class of my sample is omega j. Okay. So alpha actually relates to taking a decision in favor of a ith class. If I take, so this is used to avoid the symbol confusion. So alpha I basically relates to decision omega I. So if I take the decision, for given input x, if I take the decision omega I, then I say I have taken action alpha I. So if I take decision alpha j, that means I have taken the decision in favor of omega j. Now, when will be loss? I know that if omega j is true class, omega j is true class and I take decision alpha I, that means I have taken decision in favor of omega I. So I should have taken decision omega j, but my system is telling that take a decision omega I. That means I am doing something wrong. If that is the case, then surely I have to face some loss. So this loss lambda is written like this. Lambda is the loss when I take decision alpha I when true class is omega j. So obviously when I take a decision, say alpha j when true class is omega j, there should not be any loss. Okay, so that is obvious. So this is the loss, as I said, when I take decision alpha I when the true category is omega j. Now this is the Bayes generalization, Bayes rule, or you can say Bayes equations generalization, where you can see here probability of, this is the posterior probability, so probability of omega j given x, omega j given x, remember this is now a vector, this is not a number now, this is a vector, equal to probability of x given omega j into probability of omega j divided by probability of x. So this is evidence, this is likelihood, and this is the prior knowledge. And probability of x you obtain from your sum rule. Okay, so this is same thing, just we are allowing this small x. Earlier I used to write like this, probability omega j given x. Instead of that, now I am writing here capital. So whenever I now onwards I use capital X, it is a vector. Okay, remember this. When I use small, this is a 1D number or just real number. Now you can observe one more thing. I am writing here capital P and I am writing here small p. And then again I am writing here capital P and here small p. So this has a meaning. So whenever my probabilities are of discrete nature, say this omega j is omega 1, omega 2, omega 3, and so on up to omega c. So there are some discrete values of this omega. Okay, so when the values are discrete, the probability we write with the help of capital P. Okay, so this is the condition. When I give a condition that x is given to you, what is the probability of omega 1, omega 2, omega 3, and so on up to omega j or omega c, then there are discrete levels of omega. Okay, whenever there is a discrete thing, we are going to use capital P. Similarly, you can see here I am using capital P since this is probability of omega 1 or probability of omega 2 and so on up to probability of omega c. Again, this is a discrete level probability, so I am writing capital P. So when I write P continuous, it means that this input is also continuous, and I'm talking about continuous probabilities. Okay, so basically I'm talking about continuous probabilities. So x can take any value, say x can be 1.1, or it's a continuous thing, so it can take any value, and for each value I need to define probability. So that if that is the case, then this p must be continuous, this p cannot be discrete. So whenever there is a continuous probability distribution, we use small p. Okay, whenever there is a discrete thing, we use capital P. So don't feel that this is just a print mistake, by chance I am writing say small p somewhere, capital P somewhere. That is not the case. Whenever I write p small, it means I am talking about continuous probability distribution. Whenever I write capital P, it means it is a discrete kind of thing. Now we will see what is risk in a problem. So risk in a problem. So let alpha be a decision, lambda be loss due to a decision alpha, and R be the risk involved. Okay, and omega is a true class for a given sample. Okay, omega be a true class for a given sample. Now assume that we have taken a decision alpha I, and loss due to this is lambda of alpha I given omega j. So true class for my input was omega j, but I have taken decision alpha I. So I incurred a loss of say lambda alpha I given omega j. So expected loss or a conditional risk with taking action alpha I is given by risk. When I write R here is now risk in taking decision alpha I given that input is X. So I am writing R of alpha I given X. So what kind of decision I will take? I will take a decision in favor of a certain class provided risk is minimized. Okay, I am not interested in taking high risk by taking a decision which is risky. Okay, so for example, if R alpha 1 given X, R alpha 1 given X is greater than R alpha 2 given X. That means if I take a decision in favor of alpha 1, or that is omega 1, then my risk is say greater than the risk if I take a decision alpha 2. So what I should do? I should choose this one or this one. So obviously I should go with minimum risk. So my decision must be alpha 2. So the expected loss can be minimized by selecting the action that minimizes the conditional risk. So this risk can be minimized by taking appropriate decisions. So I should take a decision such that my risk is minimized. So how do I compute the risk? So risk is equal to summation j equal to 1 to c, that is all classes. Then I take different decisions. So this will be lambda loss for taking decision alpha I. Suppose I take a decision omega 1, then multiplied by chance of omega 1 given that input is X plus loss due to alpha 2. So this should be, sorry, this should be alpha I. Ith decision I say. So this is a generalized thing. Ith decision, then omega 2 into probability of omega 2 given X, and so on up to loss alpha I given omega C into probability of omega C given X. Okay, so this thing we write in terms of summation like this. Okay, so that will give me total, say, risk, how much risk I have if I take decision alpha I. Now the overall risk in my problem, is equal to, this is the risk that we have seen here. This risk is for given value of X. Okay, say if I am standing here with this sample X, what is risk if I take decision alpha I given X? So this is computed for this particular point. Now this overall risk is the integration of risk for all the samples or all the points in this space, every point in this space. So I need, say, double integration actually to do this. So this is right now here it is represented by a single integration, but it depends on the dimension of x. If x is 2 dimension, this will be double integration. If x is 3 dimension, this will be 3 dimensional. So for every point in the given problem space, if I calculate the risk for action alpha and then I multiply with the probability of that x itself to appear, and if I add all this, it will give me the total risk in my problem. Okay, so where alpha x is determines which action alpha 1, alpha 2 or alpha l to take over every x. To minimize risk or find a decision rule alpha x such that chooses the action with the minimum conditional risk. Okay, so we'll take example so these things will be more clear. This rule yields the optimal performance, so including the risk. Now, what is Bayes decision, modified Bayes decision? Earlier, we used to have only minimum or go with maximum probability. Our rule was go with maximum probability, choose omega I such that it has the maximum probability to win. Now what we do now, instead of maximum probability, now we have modified to go with minimum risk. Go with minimum risk. Choose an action such that you will go with minimum risk. Now calculating minimum risk, actually we are incorporating the punishment or losses due to a wrong decision as well as probability. So this is a mixture of, it's a mixture of probability and loss. Okay, so based on this probability and loss, we calculate risk and we take a decision such that this risk is minimized. I repeat what I said earlier. When I use Bayes, I was going with maximum probability. I was taking decision based on maximum probability. That means I was doing minimum error. Okay, so when I select a probability max, that means I am doing minimum error. So I was trying to reduce probability of error. So that was my simple Bayes rule. Now people found that this is not the only situation in real life. I should not just stick to, say, probability of error. There are, say, many situations when I take a decision that may involve losses. Okay, so I should not just take a decision based on probability of error. Sometimes it so happen that error may be more but losses must be less. Okay, so that is this condition I have to take into account. So when I take probability plus loss into account, I am actually doing risk management. I am trying to reduce the overall risk in my problem. So considering probability and losses. Now let us take a simple case of two category for understanding purpose, and we will try to modify the Bayes decision with incorporation of losses. Now let us have two possible actions, alpha 1 and alpha 2. So alpha 1 corresponds to a decision omega 1 and alpha 2 corresponds to decision omega 2. And let we have a shorthand notation here. Lambda ij stands for loss when I take a decision alpha I given true state or true class is omega j. So this should be a vertical line. Okay. Now the conditional risk, when I take decision alpha 1 given some input x is equal to, so this we can write as lambda 1 1. So lambda 1 1, that means actually it is lambda alpha 1 given omega 1, that is true state is omega 1 into probability of omega 1 given x. Okay, then the other reverse kind of thing, say loss, when I take decision alpha 1 given the true state is omega 2 multiplied by probability of omega 2 given x. Try to understand this equation. I am writing here once again. So this is the risk. What is the risk here? I am taking decision in favor of omega 1, that is alpha 1 is my decision. So when I take decision alpha 1, that means I am declaring my class of input to be omega 1. Okay. If I do that, what is risk in taking such decision? So it is risk of taking decision alpha 1 given input is x. Now this you can write as equal to, this is a loss. You take a consideration of loss and decision is alpha 1 given that true state is omega 1, then probability of appearing omega 1 when input is x. So this will give you risk for this half part. And the second half is, if you take a decision alpha 1 and the true state was suppose omega 2 multiplied by the probability of omega 2 given x. Okay, so this will give you one component of risk when you take decision alpha 1. Now there is another component here of risk when you take the other decision, that is alpha 2. How many decisions you can take? You can take two decisions. You can take, say, alpha 1 decision, or you can take alpha 2 decision. So what we are trying to do here is we are trying to calculate risk for alpha 1 and risk for alpha 2. Okay, then final decision we will take such that whichever is this, whichever decision produces minimum risk, we are going to take that decision. So before that we need to calculate this. So now I am writing risk for alpha 2 given x. So this I write as lambda 2 when true state is 1. So loss when action is omega alpha 2 and when true state is omega 1. So probably multiplied by probability of omega 1 given x plus loss when I take decision alpha 2 when true state is omega 2 multiplied by probability of omega 2 given x. Now these two equations, this one and the upper one, I can write in shorthand notation like this. So this is same thing. So this quantity we are writing it as alpha, say lambda 2 1. So this lambda 2 1 is nothing but this thing, and this lambda 2 2 is nothing but this thing. Okay, so similarly we are writing lambda 1 1 and lambda 2 2. So I just repeat, when I write lambda 1 2, that means I am talking about loss when I take decision alpha 1 given state is omega 2. So this first number here is decision and second number is the true state, true class. Okay, so I hope you have noted down these two equations. Now what is my decision? Decide omega 1. So take the decision in favor of omega 1 if risk alpha 1 given x is less than the risk alpha 2 given x. Otherwise, decide omega 2. So this is the simple rule that we are following now. So from equation 1 and 2, I write like this. This is nothing but risk of alpha 1 given x, and this other part, right hand side part, is risk alpha 2 given x. Okay. Now by little rearrangement of the terms, what you can do, you can rewrite this equation, let us say 3 as 4. So what we have to do, we have to take the terms which are similar to one side and then group it. Group according to this probability omega 2 given x and probability of omega 1 given x. Okay, so I hope you can do this. And then again, by doing, say, multiplying by -1, you will get equation 5. Now, this is, as you know, this is the posterior. This posterior, these two sides are posterior. We are replacing the posterior in terms of prior and likelihood. So equation 6 is written with the substitution of this posterior in terms of prior and likelihood. So this is also replaced by this quantity. So try to understand this step. So what we have done, actually, we have started with definition of risk. Okay, then we have decided, this is my decision rule, that if risk of alpha 1 given x is less than alpha 2 given x, decide omega 1, otherwise decide omega 2. Now let us have this decision first, or let us assume that this is the condition. Then in this condition, we substituted the definitions of risk for alpha 1 and risk for alpha 2 in like equation 3. Then in equation 4, we rearranged the terms of posteriors of two things in proper way. So these are the terms collected for probability of omega 1 given x, and to left hand side the probabilities of omega 2 given x are collected, and then just we multiply by -1 so that this fifth equation will appear. Now in equation 5, I am substituting posterior in terms of prior and likelihood. Okay, so if I do that, I come up with equation number 6. So what will happen is this probability of x and this probability of x will get cancelled out since it's common. So with again little rearrangement, you will land to this equation. So equation, I can say 7. Now what is this 7 equation? You see carefully, this is a decision in favor of omega 1. You remember this. You are taking decision in favor of class omega 1 if this condition holds. Okay, if this condition holds, you will take decision omega 1. Otherwise what is your decision? Otherwise you will go to omega 2. Now what is this equation 7? You just see carefully. What is this ratio? This ratio is likelihood ratio. Okay, this ratio is the ratio of two likelihoods. So numerator is probability of x given omega 1. So it is the distribution of x in omega 1, and denominator is distribution of x in omega 2. So these are two likelihood things, and we are taking ratio of that. If this ratio is greater than this loss difference lambda 1 2 minus lambda 2 2 divided by lambda 2 1 minus lambda 1 1, so this is a ratio, this is a fixed quantity. Okay, the losses are fixed for a given lambda 1 2 lambda 2 2 lambda 2 1 and lambda 1 1 case, and this posterior is also fixed. The posterior is probability omega 2. Say for a given problem, what is posterior? Sorry, not posterior, prior. It is a prior. So prior of omega 1 and prior of omega 2, they are fixed for a given problem. So this is a fixed quantity. This is also a fixed quantity. So I can call this as some theta. Okay, a fixed number. And this side, left hand side, is dependent on the input x. Okay, so if x is varied, this ratio is going to vary. Now if I say that this ratio is greater than certain or equal to certain threshold theta t, or let us say greater than t, then go in favor of omega I or omega 1 in this case. If ratio is less than theta t, go for omega 2. So it becomes now very simple for a given problem. Once you solve this formula number 7 for your problem, you will obtain a theta t, a threshold value. What you have to do is you have to just calculate this likelihood ratio for given x. For a given x, you just compute this likelihood ratio and just compare it with theta. If this is greater, then decide omega 1. If this is less than theta t, decide omega 2. That's it. Okay, so this is very simple. Once you go for implementation on, say, some microprocessor kind of a kit, you can easily do this. But before you implement, you must solve this for your problem. Okay, so what we can do is we can put this ratio on, say, y-axis, and then this x is my input here. This is a 1D case, so I am just having a small x here, and this can be theta t. So if you vary x from, say, this minimum position to some maximum position in your problem, then you may have this kind of likelihood ratio with respect to your risk. Okay, considering the risk, and this is the region, this is the region where this ratio is greater than theta t. This is the region where it is less than theta t. This is the region where greater than theta t. So whenever it is more than theta t, I say this is class 1 region, then this is class 2 region, and this is class 1 region. Okay, so like this we can classify given input. Say given input is suppose here. The given measurement right now is standing over here. Then you go to this curve and just check. Then I find that this is more than theta t. For this input, I am going to declare it as omega 1. Say omega 1 stands for some pen, then my decision is pen. Then if you are standing, suppose here, then you check the ratio. This ratio is less than theta t, then you will say, okay, this is class 2. That means it is a duster. Okay, so that way you can uh, easily classify given input. So what we have done here is we have taken into account the loss. So in my decision, loss is incorporated with the probability. Okay, so we will take one example so that these things are more clear. Now we will take this example. Suppose there is a robot. A robot needs to classify between, say, road is as omega 1 and muddy region as omega 2. So I want to do this classification between two things, omega 1 and omega 2. The prior probabilities of road and muddy region in a given scene are like this. Say probability of omega 1 is 0.4. Say 40% of the time the robot is seeing, say, road, and 60% of the time the robot is seeing a muddy region. The robot extract a texture feature metric. So there is some, say, metric which measures the texture in front of the robot. So that is helping us to distinguish between road and mud. Okay, so we can differentiate between road and mud with the help of that feature. So this is my X. It is noted that the road and mud features are normally distributed with the normal distribution 10, 1. So the mean value is 10 and variance is, say, 1. And the other one is 12 and 3. If mud is classified as road, the loss is 1000 rupees. Now see this situation. If you misclassify, if mud is classified as road, then there is a loss of 1000 rupees. Now why this 1000 rupees? Because it may destroy our robot. Okay, so the robot is suppose costing 1000 rupees, then I have to have a 1000 rupee loss if I take a wrong decision. If the road is classified as mud, then the loss is 10 rupees. Okay, if road is classified as mud, then there is a loss of 10 rupees because of some reason, and there is no loss for a correct decision. So this is the situation. Is this understood? So we have to have two decisions here. Alpha 1 which is in favor of omega 1, alpha 2 which is in favor of omega 2. Then when I say loss, if I take decision alpha 1, that is in favor of omega 1. So I am classifying road when the true state is road. So it is written as lambda 1 1. So there is no loss. Loss is 0. Then I have the other option. I take a decision alpha 2 when true state is omega 2. So I am classifying mud as mud. So this is lambda 2 2, which is also 0. Now there is the other term lambda 1, lambda of alpha 1 given omega 2. So I am taking a decision as road when the true state is mud. So that is costing me 1000 rupees. Okay. Then there is the other case when I decide alpha 2, that is mud when it is road. So it is costing me 10 rupees because of this wrong choice. It is costing me 10 rupees loss. Now what I have to do is I have to take a decision based on these losses and the given probabilities such that risk is minimized. Okay, so this is my problem. I hope this problem you understood. So we will continue with this problem tomorrow. So be ready for test tomorrow. Okay. Thank you.